pleasure to welcome Ian, who's going to talk about a very interesting subject for me, which is the automated reception of Funcube, Fox, and weather satellites using GNU radio. Go ahead, Ian.
Okay, can everybody hear me? Great. Well, for those that don't know me, as the introducer said, yes, I'm Ian Young, and yes, it is spelled correctly on the slide, not on my pass. But there we go. What I'm going to talk to you today about is, yes, automated reception of Funcube and Fox and weather satellites. A thought struck me a couple of years ago after one of these colloquiums. The Funcube dongle Pro Plus has a bandwidth of 192 kilohertz. The satellite subband on 2 meters is only 200 kilohertz, so we can grab the huge majority of it. So this talk could also have been called, what could we do with a Raspberry Pi and a Funcube dongle? So, what I'm going to talk about. I'm going to talk about the software and hardware used. I'm going to go into detail on the Funcube telemetry receivers. I'm going to say what the differences are with the Fox receivers. And I'm going to talk briefly about APRS receivers, because the APRS Fleet is on 145.825, such as it is at the moment. And then we'll talk about the weather satellite receivers towards the end and a quick wrap-up. So, the hardware, and a little bit of the software as well, actually, to be honest. Funcube antenna, just a turnstile, that's all. A wideband amplifier. There is a splitter that is to feed the Pi that we use for the weather sats from the same antenna. More of that later. The dongle Pro Plus, of course. A Raspberry Pi 3. I haven't tried the 3B yet. I haven't needed to. GNU radio, obviously. An ARISS FUNcube telemetry decoder and the Fox dashboard. So the last 3 there, yes, they're not hardware, they're software, but that's the entire telemetry receiving station. So, in order to actually receive the Funcube telemetry, we've got to acquire the signal. We've got to tune to it. We've got to filter it. We actually need to format it correctly for the decoder before we pass it to the decoder. And then we need to upload it to the warehouse, otherwise known as Annoying Dave Johnson. So, first stage, like everything, is to actually acquire the signal. As I said earlier, the Pro Plus has a bandwidth of 192 kilohertz. If we tune to 145.9, we get the whole of the band sans the 4 kilohertz at the top and bottom. This is the GNU radio block that does that. The keen-eyed ones of you, probably more of you up the front, will see it's tuned to 145.91. That was purely legacy during development for me. Yeah. So now we've got the signal. We've got a block of 192 kilohertz, yeah? So we need to tune to the beacon. Well, GNU radio has a wonderful block called the frequency translating fur filter. That is a rather grandiose term. It effectively is a big fat tuning knob. You know the tuning knob in the middle of your HF radio? Same thing. So you'll note that the frequency is 27K. What that actually means is 27 kilohertz from the center of your 192K bandwidth. So you need to do 145.91 in this case plus 27. Okay, yeah. And by the way, the signal comes in here from the dongle itself. The other thing we do here, I actually downsample it from 192K to 96. That is because the current decoder I'm using does actually need that. It needs it at 96 kilohertz. So now we're tuned onto the beacon. But, of course, this is a low Earth orbit satellite, so we've got that horrid thing called Doppler to deal with. Luckily, GNU Radio's got a RPC server, a remote procedure call server, that allows us to send and receive data from an external script. So I wrote a script that once a second calculates the Doppler and sends that information to the flow graph. And that is the GNU radio block that does that. It runs constantly 24/7. The script runs constantly 24/7, whether the spacecraft is above the horizon or not. Yes, it's nonsensical when it's below the horizon, but that way I don't have to worry about stopping and starting it. So, filtering and resampling. The resampling bit we've actually already seen, because it's also on the last slide. But we're now tuned to the beacon. We need to filter it and resample it down to 96 kilohertz. Again, that's what Alex's decoder needed. So you can see the resampler again, 192 down to 96. And we can put we just put a simple low-pass filter. This one is at 4K. Again, this would have been early in the development. I could make it tighter because I'm now tracking the Doppler. But remember, we are running on a Raspberry Pi. The tighter that filter, the more horsepower you use. And it gets computationally expensive, shall we say. It has got a transition width of 200. When I build these things on my big Intel Core 5 or Core 7, I tend to like to go down to 100 Hertz or even 10 Hertz. But on the Pi, that's not really feasible. So, formatting the signal. And Alex, if you're still here, you can correct me here, because I'm not sure I've got this entirely right, but it requires, the decoder in question just requires a signal to be mixed in with a 5K signal to shift it up 5K in the spectrum. It also requires the data in a particular format. So we basically have a 5K signal here, or just slightly over 5K, running at 96 kilohertz. Yeah? Signal comes in here. We multiply the two together. In the real world hardware, a mixer is often multiple components. In the world of software, you just multiply the two signals together. This part, the multiply constant of 48K in the complex to integer short, is just so it's in the right format for the decoder. Then what we do is we put it out to two UDP ports so that we can connect the decoder to it. So, before we go any further, this is the entire RF chain for receiving one Funcube telemetry signal. And basically, every single one of these blocks was on one of the prior slides. So, in order to actually decode the FEC telemetry, I use ARISS decoder. The way I configured it was to listen to the UDP port via a couple of Unix utilities, either SOCAT or NetCat. It decodes the telemetry packets. It pipes them all to a shell script to upload to the data warehouse. Now, there is a decoder that is almost built into GNU Radio, which is supposedly better, but I haven't managed to get the time to integrate it yet. That is somewhere on my to-do list of several hundred things. What else can I really say about that? Not a lot. Now, those of you that I haven't sent to sleep yet will notice that the previous slide that showed the entire chain only worked for one Funcube spacecraft, and I was going to talk about multiple. Well, so how do we do that? Well, the wonderful thing about SDRs is that we can duplicate the signal as you would with a splitter in the real world, but you don't get a 3 dB loss. It's an exact copy of the signal. There is no signal to noise, increase there. So all we do is, you remember this block, which is basically the block that talks to the Funcube dongle itself. Remember we had the frequency translating FUR filter? Well, we now have two. And after those, it didn't show it on this slide, but after those, you basically have copies of the rest of that signal processing chain that I showed earlier. Those of you who know Funcube 1 and Funcube 2 frequencies intimately may wonder what this one is, 7.75K. It's actually where Funcube 2, also known as UCube, shows up after you add 145.91 to it. So, okay, right, so I'll add another slide there. So, yeah, that's how simple it is to do it. Once you've got that first chain, all you effectively do is duplicate the chain for each of the spacecraft. And I actually generally run extra ones as well, so I can monitor how many packets I'm receiving without needing to hit the dashboard. So I tend to have 2 for Funcube 1, 2 for Funcube 2, and yeah, 1 is for my local display, 1 is outputting to the dashboard. So that's 4 decoders. It's 2 chains, it's 2 signal chains, because I can just, again, duplicate the data before I send it to the UDP port. So that's Funcube. Fox, well, we've got multiple Foxes as well. Oh, actually, before I go on to the Fox differences, one thing to note, if anybody does try this. Some of you already know, but NAIF 1 sometimes turns up in the same passband that Funcube 1 does. And so often my Funcube 1 decoders will actually decode packets from NAIF 1. I leave Dave to sort that out when it gets to the warehouse. So, what's the difference with the Fox telemetry? Well, Fox telemetry requires a linear receiver. It also needs a sound card, and it uses subaudible tones rather than BPSK. So, how do we do this? Well, this flow graph we see here is actually a linear receiver. Once again, we have your FUR filter. Yeah, this would have come in again from the dongle. It's just split off again in exactly the same way. This could be the 3rd or the 4th or the 5th iteration. We have a low-pass filter. We then convert it so that it is the correct format for sound cards. We need to resample it down from 192 in this case, because again that was a prototype, down to 48. We amplify it a little bit and we send it to a sound card. Now, the challenge is that of course the dashboard is expecting to talk to a sound card. So we need some kind of loopback or virtual audio cable. And Linux does have the ALSA loopback driver, otherwise known as SNDA loop. For those of you not familiar with Linux, something similar on Windows would be the virtual audio cable. It does exactly the same thing. And by using that, the dashboard thinks it's talking to a real sound card. But actually it's just talking to another piece of software. The other consideration is that the dashboard needs a GUI. Thankfully, there are fake or nested X displays that we can use, so you don't have to tie up your main display. And when you start running multiple, that can get frustrating and annoying. One thing I would say to future dashboard builders, please consider a minus no window option or something where we can turn all the fancy GUI off, so we can just run multiple of them like this. Now, APRS. Well, they're FM as well as the Fox spacecraft, but they're all on 145.825. So there's only one extra signal chain. So a center frequency of -75 kilohertz if you'll tune to the center of the subband. There are a number of TNC softwares out there. There's Direwolf, there's the original Linux sound modem, there's the even older Linux sound modem if you're brave. Because they all typically want a sound card, the same technique can be used for Fox telemetry, or as was used for Fox telemetry. It just needs wider filters, and it's an extra signal chain. That's all there is to it. And so, in summary, on a Pi 3, we can decode telemetry from the entire Funcube fleet. I will be adding JYSAT1. We can decode telemetry from the entire Fox fleet. We can receive APRS packets. And I think I've run 5 FUNcube receivers and 2 Fox receivers, all on one Pi 3, with no issue whatsoever. But what about the weather satellites? Well, they're on a different frequency range, but you can still use the FUNcube Dongle Pro Plus. However, while developing this, I found a little known limitation with the drivers. For the FUNcube dongle and the RTL drivers, once you set their frequency at program start, you can't change it. You have to stop and restart. So, a second Pi and dongle were needed. Oh dear, there's an expense that will break anybody's bank. There are 2 different types of weather satellites. You've got the NOAA APT Fleet, and you've got the Russian Meteor M2 Fleet. There was supposed to be 2 of them up there, but somebody programmed the rocket wrongly. It thought it was launching from the wrong place. Hopefully in March next year, there will be a second one actually up there, if they get that launch right. But with Wednesday's events, might get pushed back, you never know. The frequencies in question, we all know they're on 137 megahertz, but they're spread across that entire band, way larger than our 192 kilohertz. But the signals themselves will fit in to 192 kilohertz bandwidth. So how can we cope with those extra constraints? Well, the way I did it was we have a separate flow graph for each spacecraft. I wrote a scheduling script that runs at midnight, that grabs the entire passes, excludes certain ones that don't get above a certain elevation, because it's just not worth it. It sets the priority of passes in cases of overlap. Now, that sounds like an awful lot of big words. To be honest with you, highest wins, unless it's Meteor M2. So the code's actually quite simple. And then what it does is it schedules the flow graph for each of the appropriate spacecraft to start and stop at the appropriate times. It actually can start and stop up to a minute earlier in the case of start, or later in the case of stop. Really, just to make sure you cover the entire pass. Because in the case of Meteor M2, it can take a little while to get PSK lock, but once it gets it, it manages to cope quite low down, which I found a little bit of a surprise, but hey. So again, yep, due to the frequency constraints, we've got to stop and start. And what we actually do effectively is record the raw data and then process it later. That later is actually less than a minute later, because the scheduling script also kicks off the decoding part. WX to image can be used for the NOAA spacecraft, but I also do have a flow graph again from Alex that decodes the raw data and outputs a JPEG file, which is quite useful. The Meteor M2 decoding solution. Well, there's always been one for the M2, but it was always a Windows product, and you had to run it, if you're a Linux guy, you had to run it under Wine, and it was interactive, so you couldn't really automate it. However, there is now a command line decoder that is natively available for the Raspberry Pi as well as AMD and Intel chips. It does work, but beware. On a Pi 3, it will take 4.5 hours to process a pass. Yeah. Okay? Now, thankfully, this isn't actually the...
Sorry to interrupt.
Go.
Radio mic.
I'm
being waved at by the guys in the back, because we have something special coming up. We're actually downstairs attempting a contact with the International Space Station.
Golf Bravo 4 Alpha Uniform Kilo. This is November Alpha 1 Sierra Sierra. How do you copy?
Golf Bravo 4 Alpha Uniform Kilo 2 November Alpha 1 Sierra Sierra. We copy you loud and clear, Serena. Over.
Golf Bravo 4 Alpha Uniform Kilo. This is November Alpha 1 Sierra Sierra. How do you copy?
November Alpha 1 Sierra Sierra, this is Golf Bravo 4 Alpha Uniform Kilo. We copy you loud and clear, Serena.
So they are running a test at the moment where multiple uplinks are being
November
tried.
Alpha 1 Sierra Sierra, this is Golf Bravo 4 Alpha Uniform Kilo. Are you receiving, Serena? Over.
So the purpose of this is to actually figure out which uplinks work and which don't, or are better or worse.
Golf Bravo.
So it might not work.
Sorry, November Alpha 1 Sierra Sierra, this is Golf Bravo 4 Alpha Uniform Kilo. Are you receiving, Serena? Over. November Alpha 1 Sierra Sierra, this is Golf Bravo 4 Alpha Uniform Kilo. Are you receiving? Over.
It's basically to characterize the radio that is currently on board and see which combinations work.
November Alpha 1 Sierra Sierra, this is Golf Bravo 4 Alpha Uniform Kilo. Are you receiving? Over. November Alpha 1 Sierra Sierra, this is Golf Bravo 4 Alpha Uniform Kilo. Are you receiving? Over.
Yes, we can. It is beautiful and clear today.
Hello, Serena, and welcome to the concluding part of the amateur radio meeting in the United Kingdom for the Radio Society of Great Britain and the AMSAT-UK Corporation. Great to hear you.
Yes, up here it's a lovely 72 degrees all the time.
We're very envious. It's absolutely pouring with rain down here in England at the moment, but great to hear you, and would like to say the very best of luck to you, Alex and Sergey, and everyone here wants to say a great big cheer to all the crew up on the International Space Station. November Alpha 1 Sierra Sierra, this is Golf Bravo 4 Alpha Uniform Kilo. Are you there, Serena?
Yes, I agree. That was not the best news, but the good news is that the launch abort system worked, and so those two guys are safe on the ground, and I'm sure we'll get another crew up here quickly. Over.
Yes, and we're all wishing the crew on the ground as well the best of luck as well. Please say our regards to Alex and Sergey as well, and we wish you all a very safe time up on the station. November Alpha 1 Sierra Sierra.
Copy that. I'm actually still looking for Golf Bravo 4 Alpha Uniform Kilo.
In November Alpha 1 Sierra Sierra, this is Golf Bravo 4 Alpha Uniform Kilo. Serena, can you confirm your channel number, please?
Alpha 1 Sierra Sierra, how do you copy?
November Alpha 1 Sierra Sierra, this is Golf Bravo 4 Alpha Uniform Kilo. We can receive you, Serena. Can you confirm your channel? Over.
Golf Bravo 4 Alpha Uniform Kilo, this is November Alpha 1 Sierra Sierra, how do you copy?
November Alpha 1 Sierra Sierra, this is Golf Bravo 4 Alpha Uniform Kilo. Are you receiving, Serena?
Yeah, is this Golf Bravo 4 Alpha Uniform Kilo?
This is Golf Bravo 4 Alpha Uniform Kilo. Serena, are you receiving? Over.
Golf Bravo 4 Alpha Uniform Kilo, this is November Alpha 1 Sierra Sierra, how do you copy?
November Alpha 1 Sierra Sierra, this is Golf Bravo 4 Alpha Uniform Kilo. We're receiving you loud and clear, Serena. Can you copy? Over.
Yes, this is November Alpha 1 Sierra Sierra, is this Golf Bravo 4 Alpha Uniform Kilo?
November Alpha 1 Sierra Sierra, this is Golf Bravo 4 Alpha Uniform Kilo. Are you receiving, Serena? Over.
Yes, hello, this is the International Space Station. How are you?
We're good, thank you, Serena. Can you confirm this? You're talking to Golf Bravo 4 Alpha Uniform Kilo, over.
Yes, I'm looking for Golf Bravo 4 Alpha Uniform Kilo.
November Alpha 1.
Oh, back it.
If they're expecting to be on 2 meters on the uplink, I'm not hearing them here.
Yeah, so there is multiple channels, and they are switching channels during the test. So if they are switching channels, and somebody else is obviously calling on one of the
Sierra,
channels.
this is Golf Bravo 4 Alpha Uniform Kilo. Are you receiving, Serena, over?
Yeah, I think this is getting close to the end of the
Golf
pass.
Bravo 4 Alpha Uniform Kilo. This is November Alpha 1 Sierra Sierra. How do you copy?
Golf Bravo 4 Alpha Uniform Kilo. This is, NA1SS, this is Golf Bravo 4 Alpha Uniform Kilo. Do you copy, over? Golf Bravo 4 Alpha Uniform Kilo. This is NA1SS, this is Golf Bravo 4 Alpha Uniform Kilo. Do you copy, over?
I don't think this is.
Yep, this is November Alpha 1 Sierra Sierra. How do you copy? Copy you loud and clear.
November Alpha 1 Sierra Sierra, this is Golf Bravo 4 Alpha Uniform Kilo. Are you receiving, Serena, over?
Yes, I finally have you. This is the International...
That's great, Serena. Thanks very much. Sorry for all that confusion. Just a very quick hello from the Radio Society for Great Britain and the AMSAT Colloquium here in the UK, just drawing to a close. Everyone here wants to say a great big thank you to yourselves, and the best of luck to you, Alex and Sergey. Over.
Thank you so much. It's been an interesting week, but it's really fantastic talking to you guys. Over.
Okay, thanks very much, Serena. We're just about to hit LOS here, so we'll sign off and we'll say thank you very much, and everyone wants to give you a big cheer. Over. Go.
Thank you very much. Have a great day down there from the International Space Station.
Golf Bravo 4 Alpha Uniform Kilo says signing off from the international from the contact with the International Space Station. Over.
Golf Bravo 4 Alpha Uniform Kilo. So long from November Alpha 1 Sierra Sierra.
Well, that was interesting. Right, always works at the last minute. So well done to them downstairs. Back to Ian.
Am I hot, yeah?
Yep.
Yeah. Am I? Yeah, okay. Right. Before more important things came along. Decoding Meteor M2. Yeah, as I was saying, there is now a command line decoder available that you can automate with cron, etc. It does work, but as I said, 4.5 hours to process a pass. But there are only 2 decent passes a day for any one place on the Earth, and one of those is most likely going to be in darkness anyway, so at the end of the day, it's not the end of the world. As long as you don't want to compare your received picture with what the BBC are putting out on BBC News 30 minutes later. So, with this system, or this type of system, what else could be done? Well, with HF upverter, weather facts from Northwood and Germany and other places could be decoded with the assistance of FLDigi, because FLDigi now has a remote control facility as well. Also, again, using FLDigi, you could decode the Navtex messages on 490 and 518 kilohertz. And yes, I've done both, but I haven't automated it yet. Next step for me is really to just add the future FUNcube and Fox spacecraft and add future Meteor spacecraft if it manages to get to orbit this time. Hopefully it will. Add the third pi, as I mentioned, for WeatherFax and Navtex. Use the GSAT decoder rather than Alex's. Alex, I don't know if you're back in the room. I saw you wondering about it earlier. But I think even Alex agrees that the one that is built into GNU Radio now, or available to be built in, is better than his. And yeah, send weather pictures to a web server, but also, because we can run multiple decoders relatively simply and relatively cheaply, I'm toying with the idea of sending the telemetry values to RRD tool for onward graphing, locally. And I think, yeah, that's it. Does anyone have any questions?
Okay, well, Leslie, thank you very much for that.
No problem.
Very good presentation. Sorry about the interruption. But
no, don't worry about that.
I guess no one can wait for a spacecraft in orbit. It won't stop for you, will it? So,
someone should have a word with Newton.
Yeah.
Or should have had a word with Newton a long time ago.
Who has a question for Ian?
And no heckling from the string.
Thanks for lecture. First, a small advertisement. I wrote Meteor M2 decoder, which is command line based, but it's unfortunately written in Java only. But I think you could figure out the logic in the writing in the radio. The question is, have you ever observed a change in a satellite frequency of a transmitter? So on spec it might be one frequency and
yes,
at some pass. What did you do there?
Well, with Funcube 1 has that exact problem. I don't think I'm giving any secrets away. When it comes out of Eclipse, I can't remember if it's higher or lower than where it should be. I've never managed to totally characterize the behavior. It takes a little bit of time to get warm, and then it's fine. All I did there was increase my filter. So I suffer with slightly less signal to noise post the filter stage, but it allows me to pick up the very early part of the pass. Now in my case, depending on the pass, it's not a problem, because if it's north coming south, I've got a hill in the way. So by the time I can see it, it's warm enough, but if it's south to north, it's annoying. So again, one thing I might well do to improve it is automate that a little bit, because I can change the filter bandwidth on the fly. So I may well do that, so that the rest of the pass I can have the very tight filters, which just increase the signal to noise ratio, which, as long as you don't cut off any of the information, then will give you more decodes.
Okay. Any more questions? Doesn't look like it. Again, well, thank you very much. That was a really good presentation.
Thank you.
Before we all go, though, Jim would like to make an announcement or two.
Thank you very much. I won't keep you more than 2 minutes.